That was the moment of explosion, the Big Bang.
But how do we know? Let's travel back in time to unraveling the mystery that all started with a Big Bang Bang!
This is the cosmic microwave background. This is the leftover radiation from the Big Bang, the big explosion after which the whole of our universe came to be. Today, it is widely accepted that the universe started with a Big Bang. However, this idea has been around for less than 100 years. At the beginning of the 1900s, it was understood that our Milky Way was at the center of our universe, and every astronomical objects we could see belonged to the Milky Way. Nothing existed past its outskirts. Based on this knowledge, Albert Einstein developed a scientific model to understand the structure of our universe, and he proposed the idea of a static universe, a universe that was neither expanding or contracting, infinite in both space and time. However, around the same time, scientists started realizing that there existed objects past the Milky Way. Slipher and Hubble were the first to recognize that those nebulous objects were indeed other galaxies that lived beyond the realm of our own. Further, Hubble realized that these galaxies were moving away from us at increasing speeds. Based on these observations, in 1927, Georges Lemaître proposed that the observed recession of these galaxies was due to an expanding universe, a universe that had to start with a Big Bang. A few years down the line, in 1940, a team of scientists at Princeton University, George Gamow, Ralph Alpher, and Robert Herman, predicted that if the Big Bang actually happened, its radiation should permeate the entire universe, and it should be detectable by a microwave antenna. And guess what? Only 25 years later came the first observational proof of Lemaitre's idea. Working at the Bell Laboratories, Arno Penzias and Robert Wilson were trying to build this very sensitive microwave antenna to be used for satellite communications. To their surprise, no matter where they pointed this antenna, they detected this background radiation. This noise to their data was uniform no matter where they pointed the antenna. So it couldn't be produced by something on Earth. For example, it couldn't come from a city where human activity, such as microwaves, could produce a detectable signal. And it couldn't be produced by a particular source in the sky, such as the sun. It didn't take long for them to meet the Princeton team and together realize that that noise was in fact the predicted microwave background. In 1978, Wilson and Penzias were awarded the Nobel Prize in Physics. So now you may be wondering, why does this particular picture represent the proof of an explosion, right? Alright, let's first walk through the Big Bang Theory. This is the most widely accepted scientific theory that tries to explain the birth of our universe and all the events that transpired afterwards, leading to the universe as we see it today. At the instant the Big Bang sets off, the universe is an incredibly hot, dense collection of matter and radiation. Light is transforming into elementary particles of all kinds, which then collide with each other, becoming light again. Soon after, another major event triggers a huge release of energy. Every bit of the universe, the size of an atom, becomes the size of an orange. This sudden expansion carries the name of inflation. We are now in a universe that is expanding and cooling down. And it just got cold enough for particles such as protons and neutrons to form and survive. Those protons and neutrons are the very ones that make up our bodies. As the temperature of the universe drops, Protons and neutrons start to fuse into the lightest possible atomic nuclei. Within 5 minutes, the chemical content of our universe's history is set. 75% hydrogen, 25% helium, and a little tiny fraction of slightly heavier elements. It's only thanks to stars and the nuclear fusion in their core that later on, heavier elements such as the oxygen that we breathe or the gold in the necklace that you're wearing were produced. As Alex told us,
we are made of star stuff.
In a universe filled with light, a plasma of electrons, and atomic nuclei mostly of hydrogen and helium, all that's left to happen is for it to expand and cool down. When the temperature of the universe reaches a mere 3000 Kelvin, atomic nuclei can attract the necessary electrons to form stable and neutral atoms. When the electrons are trapped in an atom, they can no longer collide with light, interfering with its path. Thus, light can freely travel across the universe. The universe's 400,000 years birthday is the moment when light can finally travel freely in an expanding universe, marking the end of the Dark Ages. As matter is filling up our universe, gravity starts to take over. Elements start conglomerating into clouds, which will later become stars, which will later attract each other to form the first galaxies. About 10 billion years or so later, a little star appears on the outskirts of the Milky Way, our Sun. How do we know that this is actually the path the universe took? Well, what's amazing about technological advances is that we have been able to experimentally prove many of the theoretical concepts we just described. So the Big Bang isn't just our best guess at explaining the birth and history of our universe, but it is the most widely supported theoretical interpretation by a long shot. But wait, I forgot to tell you what the cosmic microwave background has to do with anything. Okay, let's rewind the video. Okay, stop right here, yes. The universe is 380,000 years old. The temperature is 3000 Kelvin. Light can escape. So if light can escape, we should be able to see it, right? But what should it look like? Alright, let us assume that at this point in time, the temperature of the universe is uniform. So every point of the universe is at 3000 Kelvin. So we should be able to see this light at red wavelengths. But why isn't our night sky as bright as our sun? Well, the Big Bang theory predicts that in the meantime, 13 billion years, the universe has expanded by a factor of 1,000. If the expansion actually happened, the wavelength from the very first light should have stretched by a factor of 1,000 as well, and we should be able to see it at microwaves. Let's put our microwave goggles on and look outside. There it is! The cosmic microwave background! Since before this point, light was not free to roam around, we will never be able to see past it. The cosmic microwave background is the farthest we can see into the past of our universe.
As a scientist, I have to tell you that the Big Bang theory cannot be proven beyond a certain point. First, we will never be able to see past the cosmic microwave background, as light before it couldn't travel freely to us. Second, it is an extreme challenge to recreate the physical condition of the very early universe in a laboratory on Earth. Particle accelerators have been able to prove the physics of the 10 to the minus 10 seconds after the Big Bang, but we're reaching a limit. However, if you think of it, it only took us 100 years to go from our Milky Ways at the center of the universe to we now have a scientific theory and observational proof that tells us that our universe started with a Big Bang. So you can imagine that in a future not too far away from today, scientists are gonna be able to prove even more hidden mysteries behind the Big Bang. Thank you for watching, and don't forget to like, share, and subscribe. Bye!